Hello everyone, my name is Jakub Tomczak and today I would like to tell you a little bit about deep generative modeling and foundations of this kind of models. And before I start, I would like to thank the organizers for giving me this opportunity to talk to you. And before we start, I would like to make some, advertisement. So if you're interested in deep generative modeling, please take a look at my blog, where you can find a lot of useful information, and even further, you can maybe be interested in my book that will come up in February 2022. Hopefully, it will be available through Springer publisher. All right, so let's start. So before we start talking about deep generative modeling, it's actually very useful to think about what is intelligence in general. And I have no clue. And I'm not a psychologist, I'm not a cognitive scientist, I am an AI person, a machine learning researcher. So of course, we will not delve into different definitions and the different understandings of what the intelligence mean. But we'll really look at that from this perspective of AI, all right? And that what is useful for us. And so what is, instead of thinking about what is intelligence, we'll think about what is artificial intelligence, how we understand that, and how we can define some useful concepts to define artificial intelligence. So let us think about this very simple and general scenario. Let's say that we have some kind of environment, and we have our AI system somehow embedded or interacting with this environment. I'm not talking about reinforcement learning. However, this will look a little bit like that, but I'm really talking about very general scenario that our AI system could be a robot walking in a maze, but it could be a system, AI system supporting, a browser. It could be, a medical imaging tool that helps or assists a doctor with making decisions, right? And so on, so on. So it's really nothing about maybe some kind of training loop. Training could be completely static. So once you have given some data, the AI system just starts learning from this data and not necessarily training constantly online or something like that. All right, so we have some environment, we have an AI system, and AI system wants to take some actions or make some decisions that actually influence maybe somehow the environment, or just take some actions that just change something, but not necessarily environment. And then it gets the feedback information that could be displayed somehow to this AI system. And this is very, very basic, right? So we have these decisions or actions, and we have some information back. So this is something that we very, in a very intuitive way, we understand how it works, how we work, right, in our work. And of course, this information is possibly represented using bits, right? And I'm doing this on purpose because I want to make some seed in your head that, all right, information bits, so probably or you can predict what is going on in a second. All right, so this is the very general scenario. And so if we have information somehow inside, right? So we need to think about these three super basic components. So information processing, right? We need to somehow retrieve the information from the environment and just process it somehow. Then we have information storing. It could be, in terms of physical, in physical terms, so on some hard drive, or just simply conceptually. We need to somehow memorize what's going on, right? And then we have information transmission. So it could be communicating with other AI systems. It could be communicating with the human manipulator, and so on, right? So these are the three core components. And of course, last but not least, we have decision making, right? So if we talk about artificial intelligence, so first somehow the information must be processed, but also decisions must be taken, right, or made. So it's these two components. I would claim that they constitute intelligence, all right, or at least artificial intelligence. And when we talk about these four concepts, of course, there are some other concepts, associated concepts popping up. So, all right, what about learning, right? Information processing, storing, transmission. Actually, this is in looking at it from other angle, we can say this is actually something about learning. If we talk about learning, we have knowledge representation. So how we actually should store, how we should represent the knowledge, right? So information retrieved and so on. When we have knowledge representation, we can start talking about models and even mathematically, right? So modeling, and then how to translate them to maybe some hardware and so on, so on. So these three concepts appear very naturally if we think about this for components, right? Information processing, storing, transmission, decision making. Of course, why I can now start talking about some other related ideas, but of course, pardon, this is I think that just to make you see that these ideas are somehow intertwined or connected. And now, if we look at it from this perspective, and very, let's say, accepting for a second this very informal definition of artificial intelligence. So the question is how to formalize the problem of AI. What does it mean, right? When we have an AI system, what does it mean that what we are trying to do, right? Here. So we will look at it in a second. But before we do that, it's good to go back and think about what information means, right? This is a quick recap looking at Professor Claude Shannon, or he is actually looking at us. And if you don't know, it doesn't matter. So please stay with me. If you know, so just relax and just refresh your memory. So how we can quantify information? Let's say we have a random source of data. Something is appearing. We can think of bits or some other symbols or some continuous values and so on. For instance, we measure something, right? The question that Claude Shannon, of course, others, Wheeler, etc., asked about information was, what about uncertainty of this source, right? And how we can measure it so we can really provide some number instead of looking at maybe extremely complicated data distribution. Maybe we can provide one single number and this will tell us something. And this something is the entropy. This is the measure of uncertainty, no messiness of this data. If we always get the same number, there's no messiness, right? There's no uncertainty, and entropy is minimal. If every state is equiprobable, so every single state can appear with the same probability, we get the maximum of the uncertainty, right? And the entropy is maximized. So entropy is maximized if all states are equiprobable, and the minimum is achieved, and entropy is minimal when the probability of one value is always one, right? So these are very nice properties of entropy. And another very nice property of entropy showed by Claude Shannon is that actually, if we think about transmission of information, so optimal message length is actually the entropy. So Shannon showed that actually you cannot do better if you want to send a message better than the entropy. So the entropy will tell you what is the optimal length, so the number of bits, for instance, that are required to send a message. So, okay, so we made this first step towards quantifying information, right? And if we say quantifying something, it means that we can start thinking in mathematical terms, how we can define the problem of AI, because this is what we try to say. Now, of course, we can introduce two random sources of data. And now we can ask, all right, can we still use the definition of entropy to actually quantify uncertainty of these random variables? And the answer is yes. We can calculate the joint entropy. And moreover, we can even define the conditional entropy. So what is the entropy of one random variable given already some information about the other random variable? So please notice that actually in this definition, we have in the conditional entropy definition, we still need to use the joint distribution of two random variables. All right, that's fine. But actually, this joint entropy only covers one aspect of the reality, let's say. So this is how messy are these two random variables appearing together. But can we say something about what is the, something shared between these two random variables? And here mutual information comes into the game, because mutual information tells us how much information is shared by the two sources, right? So here, this is a very nice diagram. So we have this shared information between two random variables, right? Why this is important? Well, if we think about decision making, of course, we would like to have that one random variable shares some information with the other random variable. Or when we talk about representation learning, we want to have some representation of data that is, useful for representing data, but also is useful for some downstream tasks like classification, for instance. All right, and then it turns out that we can express the mutual information using the marginal entropy minus the conditional entropy. All right, so now it's very nice because we can having this define these entropies for random variables, we can actually define something else, right? So some other quantity, this mutual information. And mutual information is very useful because it tells us how much knowing one source of data reduces uncertainty about the other. Okay, again, if you think about decision making, so if I know some piece of information, and then it's probable that or possible that actually I will know more about the other random variable, and then my uncertainty about the world reduces, right? So keep it in mind, because now we will say about artificial intelligence finally, and why I started talking about this, entropy and mutual information. So let's say that we have two random sources of data. We have, let's say, images, and we have some decisions. So for instance, classifications, right? And also, if we talk about our AI system that looks at the environment, right? You can even think about yourself as a kind of artificial intelligence system, right? So let's say that we are this model, or we have a robot, or a smart, intelligent browser, or something like that, or some decision making. Yeah. For instance, a doctor assistant, an assistant that will take an image and make some diagnosis. So I claim that actually the goal of AI is to maximize the mutual information between our data sources and the model, right? So in other words, the model wants to understand as much as possible about the surrounding world, okay? And I can quantify it by using mutual information. And I can say that, well, if my model is capable of containing as much as possible about the world, then it achieves its goal. Namely, it knows everything about the world. It's a little bit like a scholar or some professor, right? Or PhD students. We want to learn as much as possible about this given subject so that our uncertainty drops, right? So our mutual information about our understanding of the topic and the topic itself is as small as possible, right? Right. And so if we now look at this definition, right? So I just rewritten what we had before using these three, let's say, random objects, X, Y, and M. So now we can start thinking, all right, let's say that this is our problem. And if we look at the first part, the entropy, the joint entropy, we see that the entropy of the world, right, is not influenced by the model, right? So it's in some sense saying that the world is as it is, right? And we cannot do much about it. I think a second ago I said that we want to minimize material information. Of course, we want to maximize. Sorry. So yeah. So going back, so we have this entropy part about the world. We can't do much about it. The world is as it is. You know, if you are a Buddhist, probably you understand this concept more. It's something like you cannot influence the world in any way. It is as it is, right? But then there is the second part, the second entropy, that actually is conditional, the conditional entropy between the world or the environment and the model, right? And here our model can do something about it, because here, take a look, we maximize the nutrient information, but here we have the minus sign. So we want to minimize this entropy, okay? All right, let's focus on that. Let's zoom in. So the goal of the AI, this is what I claim, is to maximize the nutrient information. So in other words, it's to minimize the conditional entropy. So minimize uncertainty of the world for a given model, right? So if, in other words, if I have a perfect model or nearly perfect model of the world, my uncertainty will be close to zero, right? So that's a good thing. And now how we define this conditional entropy? Well, we have this joint distribution over the world, images and decisions, for instance, and our model. And then we have these two components. Thanks to the logarithm, we can, of course, take the product, we can turn into a sum of logarithms. So we have this logarithm of P of Y given X and the model, right? And we have P of X given model. Right? What does it mean? It means that actually we have naturally there are two components popping up. So we have this, we can say, a model for decision making, and we have this model for understanding the world. All right. And by understanding the world, I mean that these are just some objects like images or sounds or some actions, some structures, right? And these are decisions. So we naturally have these two components, okay? So I would claim that in order to achieve, this goal to minimize the uncertainty of the world for a given model, the AI system should focus on learning two models, right? First, a model for decision making and a model for understanding the world, all right? So this is my takeaway message. This is my perspective, right? And of course, we can disagree, we can debate, discuss about it. But I think this is something very natural that that comes out from this, short discussion, let's say, all right? And I want to convince you that actually what mostly is done in AI is not the full picture, all right? And that's why we need to talk about deep generative modeling, because generative part is about actually understanding the joint or learning the joint distribution. Please remember that if we take these two distributions together, we have the joint distribution of X and Y for a given model, right? So in other words, we learn a model of joint distribution factorized in such a way, right? All right. Now let's maybe you are puzzled a little bit because most of the talks you've heard and in general what you hear about AI is about actually making decisions, taking some actions. So it's mostly about this orange part. However, I want to tell you that this is not necessarily true. And many papers in machine learning are about generative perspective. But I think it's way easier to learn a decision-making model rather than training a joint model. So what I want to convince you is that we should look at these two models together, or actually we shouldn't forget about this green model. Okay. Ooh, okay. So Jakub, you are talking, and why is it true? So I want to give you a couple of examples that will hopefully convince you to the full. So the bulk of AI is focused only on the decision-making part, right? So there's one very nice example. I will show you a few. So, but this example I love. So let's say that we have perfectly trained model that can classify images into 3 classes: a dog, a cat, and a horse. And this is really well trained, right? The problem is that when we add some noise, it could be some adversarial attack, but it could be even sometimes even a white noise or some, noise that is some noise. Okay, our model can end up giving completely crappy wrong answer, right? And instead of saying that this is a cat, it can tell us that this is a dog or a horse. Okay, and why is it so? It is so because neural networks, if we take neural networks, of course, this is the most common approach. If we train a model that is a neural network, it will look at it learns some correlations, right? Every single layer learns some correlations. And of course, by stacking a lot of layers, we learn this, very complicated correlations, right? But then if you think about it, think like a machine for a second, right? So if you take one pixel, RGB pixel, and you now suddenly change these values a little bit, and you change all these values, all pixels a little bit, then your trained neural network in the first layer suddenly gets slightly different values, some different numbers. And all these correlations together, they can give you slightly different output. And then you proceed layer by layer, right? And so all these different numbers, they will start changing, and then they can completely flip the class or the decision. So even a little noise, and it was already, I think, reported in 2016 or even earlier, even small noise can completely change the output. And what is even worse, your model could be very, very confident about it, all right? So confident, I mean, it can give you a very high probability of a wrong class. However, for us human beings, this is something like easy to see. There's still a cat. All right, another very nice example. This is stolen from Stanislav Fort and his blog post. So with this very famous OpenAI model clip, we see that there is a photo or an image of a dog, most likely, and the model is very good about it, and it predicts that this is a dog. But suddenly, if we put a sticker to that, okay, saying this is a bird, right? So suddenly, just adding these pixels, suddenly the model freaks out and it says, "Oh, this is actually a bird," because the text says that this is a bird. Then, if we do even some adversarial attack, so we add some, predefined, very nasty kind of noise, right? We can fool it completely, and if we give this noise from an image with a frog, so then suddenly the model says this is a frog. So it fails completely, all right? So now the question is, can we do something about it, all right? Remember, these all models were about learning P of y given x, right? So I would say, yes, we can do deep generative modeling. To be honest, we are still not there yet, but in my opinion, this is the way to go, right? So why do we need deep generative modeling? Another example, okay, even simpler. So let us imagine that we have two sources of data. So I mean, we have two classes, orange triangular objects and blue squarish objects, right? And we have some new data point, this big X. And this is our data. What we can do, we can first fit a model to that. In this case, I just used naive Bayes, very nice classifier. And we see that, well, it distinguishes these two sources of data perfectly, right? And we have beautiful decision boundary. So if now I ask you, what is the label of this blue, of this black cross? Probably most of you would say, well, obviously this is blue, right? Because this lies on the blue part, and this is far away from the orange part. So this model actually says so. It says, yes, this is with very high probability, almost certain, almost one, this is blue. But I would say, well, this is not necessarily true. And why? Because if we think about what is the probability of the object itself, so what is the P of X here, right? If we fit now also a mixture of Gaussians, so we fit to each model a Gaussian, right? So P of blue given X will be still high because it's further away from the orange region, but P of X, so probability of this black cross, it's actually very low because it is far away from the, say, cluster of these points of our data, right? I think that we all agree with that. So this black cross is actually a clear outlier. In this 2D, we can see it very clearly, right? And if we think about the joint distribution, P of X and Y, probably because the P of X is really low, we will get very uncertain decision because the probability will drop significantly, right? And now I hope that you see how this slide, this simple example, connects with this, whole discussion about this, what is the goal of AI? So I claim that if we want to have a successful AI system, we cannot just focus on P of Y given X. This is only a part of the story. We should also focus on this P of X, right? And how we can learn it. And typically, this is the topic of deep generative modeling. However, for me, deep generative modeling is about really learning the joint distribution, while P of X is only a part of it, right? So it's not like what we are doing in deep learning and learning this P of Y given X is some, crap, and we shouldn't do that. The opposite, we should do that, but we should also think about how we can combine it with P of X so that we can get this joint distribution. And I think this is the most important and the most interesting question, all right? But all right, so as I said, so I will follow this more typical approach. So what is deep generative modeling is about, how we can learn this marginal distribution. And in recent years, and I mean the last 5-6 years, we have really a huge, or maybe even 7, we have a huge improvement in terms of learning this P of X, this so-called density estimators. And we can divide it into more or less these subclasses. So we talk about autoregressive models, like for instance, pixel CNN. We talk about flow-based models, like real MVP, GLOW, Western normalizing flows, and so on. We talk about latent variable models, where we have these other 2 subgroups, like implicit models that we don't explicitly define a probability distribution, like GANs. We have also these prescribed models, like for instance, VAEs or diffusion-based models. And we have also another group, energy-based models. that use a bit different philosophy, right? And if we look at these groups of models, so we can, and this is very, subjective. This is just my perspective, all right? But we can think about, we can try to characterize these models, and we can say, all right, we can think, what about training these models? What about whether we can calculate the likelihood function? What about sampling, right? Can we sample, synthesize data from these models? What about compression? Can we use these models for compression? So really data compression. And what about representation learning, right? So if we look at this, let's say, criteria, qualitative criteria, so autoregressive models, the training is definitely stable, so we shouldn't have any big issues. We can calculate the likelihood function exactly, but sampling is slow because it is this autoregressive fashion how we do that. Compression we can use for lossless compression because there is no some specific bottleneck. So also we don't have necessarily some representation there, okay? However, this is possible, but it's not very straightforward, okay? When you look at these flow-based models, training is stable, the likelihood function is exact. Sampling is, depending on the dimensionality of the input, could be slow or fast and the size of the model. Compression is about lossless because we don't change the dimensionality of the input, and we get at the end some representation, right? This is the same dimensionality as the original input, but definitely we have some representation, something processed. Implicit models like GANs, training is a mess, all right? I know that there's a lot of improvement, but it is a mess because we don't have the likelihood function, but we have some adversarial loss from min-max optimization problem. This is messy. Sampling is typically very fast. We can use it for compression, actually. We can use it for so-called distortion, but in general, it's hard to think of GANs as a useful tool for compression because, we don't have the likelihood. And as I said, what Shannon said, the optimal length is actually the entropy. And if we don't have the probability explicitly, this probability distribution, well, it's problem to calculate entropy. And because the latent space used in GANs, well, it's not necessarily a representation, right? So it is, of course, I'm not saying that there's not even a single paper stating the opposite, right? I'm just telling you the common sense, let's say. Then we have prescribed models like VAEs or PCA, probabilistic PCA. So prescribed models are models that every single distribution is fixed in advance, okay? And these models are stable during training. Well, the likelihood function is typically rather approximate because we have some integrals that are really hard to calculate. We'll talk a bit about it in a second. Sampling is rather fast because we have some low dimensional representation. So we have representation and then we can project it back to high dimensional space. Compression is typically rather lossy because, as I said, so we have this bottleneck in the middle. And finally, we have energy-based models. For them, training is rather stable. However, we cannot calculate the likelihood because there is this normalizing constant, so-called partition function. And well, it is extremely hard to calculate it. Sampling is typically slow because we don't have the full distribution. We have only the unnormalized, so we need to use some kind of sampling procedures. For compression, it's rather not very useful. However, as I said, you can probably find a paper or two or a few papers that can do something with energy-based models. And for representation learning, definitely we can use them, like the first models like restricted Boltzmann machines, right? So this is the more or less very quick overview, but the question is, where can we use them, right? So for text, like text synthesis, all kind of chat box. This is where this P of X is very useful because it can take some input and maybe produce some text, like I don't know, how are you? I want to do this, and so on. So we are getting really better and better with that. Of course, images and audio generation. So this is something that definitely you probably have seen already hundreds of times or thousands of times, including very recent development deepfakes, right? So they combine both. And as you can see, we are extremely good at that. It's a little bit scary, but yes, we achieved a lot. Also for graphs, for instance, chemical structure. So this becomes an enormous topic these days from DeepMind, Microsoft, etc. So for drug discovery, 3D structure discovery, molecular dynamics. So deep generative modeling definitely plays a crucial role because without generative modeling, without understanding the structures, right, we cannot do much about it. And there are way more applications. I want to delve into them, but reinforcement learning, you know, these word models that use generative model inside, active learning for, you know, asking, like with this example, with this big black cross. So for instance, if I know that P of X is really slow for some model, so maybe this is good to ask about it, right? And medical imaging and you know, all different kinds, astronomy data, weather forecasting. So you just name it, all right? It seems that, and I'm sure about it, but it seems that deep generative is useful. And I'm telling you that this is definitely useful, and I'm telling you why, right? Before we jump into topics more concrete, we will discuss a few of these classes, not all of them because of lack of time, but some, let's say, some basic rules for deep generative modeling. So generative models actually take advantage of probability theory. So probability theory is, let's say, the language of generative modeling, and we definitely use two basic rules. The sum rule, so that we can marginalize out, sum out one random variable to get from the joint distribution to get the marginal distribution. We can do the same with y here and x here. The product rule says how we can factorize, or in plain words, how we can re-express the joint distribution using the conditional and the marginal distribution. We can do it in two ways. Then typically we work with the likelihood function, or rather the log likelihood function, because, you know, the logger changes product into sum. And if we have IID data and some model, we use the log likelihood function. So this is typically our objective. So if we want to find the model or parameter values, we maximize the log likelihood function, or we minimize the negative log likelihood function, right? Because taking the negative function, it changes maximization to minimization. And basically most, if not almost all, optimization methods by default, they minimize, because we can always make this trick. All right, so this is, let's say, the end of the first part. And this is really the introduction. And now I would like to very quickly go through three groups of deep generative models, just to give you some feeling, and that you know, you can maybe study them more in depth afterwards. All right, so let's start with autoregressive models. Right, autoregressive models are extremely useful for many applications, and they are extremely powerful, actually. So they were, in my opinion, the first models that made this big breakthrough in deep generative modeling, or made deep generative modeling very appealing, right? So what these models are about, okay? So all the time, of course, we want to model this P of X, right? So the joint distribution of surrounding variables. Through these slides, I talk all the time about images, because for images, we don't need to have some, you know, background knowledge, or we don't need to have some, you know, very vivid imagination or something like that. It's very, very simple. Just we have images, all right? So let's think about images, RGB images. So how we can express this joint distribution? Well, we can apply the product rule, right? We can apply the product rule. So let's say that we take the first pixel, then we take the second pixel, then we take the third pixel, and so on, so on. But the product rule tells us that if you take the first pixel, you should condition on everything before. Well, we don't have anything, so it's just the probability of the first pixel. When you take the second pixel, we should condition it on everything before, so the first pixel. So third pixel is dependent on the second and the first, right? So this is what the product rule tells us. And actually, autoregressive model, it's autoregressive because it looks all the time at what was before, right? Now, of course, the question is, and of course, the training objective is very nice and simple because we take the log likelihood and we can factorize, we can change this factorization into summation, right? So this is very nice. But of course, now the question is how we can model it, how we can model the conditionals efficiently, because this is the core, right? Theoretically, we know this is just this equation, and that's it. And we can, code it up. We have everything: training objective, we have sampling, and so on. But how we can model that, these conditionals, right? So the first approach would be super naive. We train all of these conditionals separately. But all right, if you think about it, so we would require, if we have, let's say, big D pixels, we'd require big D models. And each model would have increasing complexity because each model would be dependent on everything before. So you see that actually the model would be enormous and it wouldn't fit probably any memory, even for this freakingly small images like MNISTs for less than 1000 pixels, you would require 1000 models. And the last model would require, of course, 1 pixel less than the full image. So this is definitely a huge waste of memory. All right, I said memory, so we can actually use something that has finite memory, right? So we can actually use a shared model for every single conditional. We can use one single model with the same shared parameters across all pixels. And we can say, right, so let us consider this model that will look only at these 2 last pixels, right? So it will be P of, let's say, the P of D condition on P of XD minus 1, XD minus 2, right? It is extremely easy, but this is extremely limiting because we would look only at 2 pixels. Why not look at 10 pixels? Why not about 20 pixels, right? How many we should take, okay? So this is a very, very good, there are very good questions. And definitely we don't look at the full, right? And also maybe one simple, very quick explanation. So if we want to predict for, let's say, this pixel probabilities, we cannot look at this pixel because we don't have it, right? So this is the causality. So we should look only at the previous 2, right? Because otherwise we would break this. Remember, this smaller than D means that it excludes D, right? And then we produce probabilities. For instance, for categorical, it would be like having MLP and then softmax on top, right? All right, so the second approach, we can use recurrent neural nets for long-range dependencies, long-range memory. So we can actually share previous context, right, or state, and we can have this recurrency. And this is actually very, very nice because at least in theory, this is easy. This is about long-range dependencies, but this is very sequential, right? So this, if you think about implementing that and for images, it would mean that to process one single image, we need to take pixel by pixel, storing the states, passing them and going like this, and it would take forever. And moreover, with RNNs, we can have this problem of vanishing gradients, right? So nice, but thank you, but no thank you, right? And then the big breakthrough, also thanks to, among others, now Kalkbrenner, appeared when actually these people figured out that, wait a second, we can actually process pixels using convolutional layers, a special kind, causal, because convolutional neural network takes pixel in the middle and have this, let's say forward and back path, these two. So we cannot look into the future. So we have to cut our convolutional layer, and we must ensure that this is causal. So it doesn't look at this at the first layer, doesn't look at the same pixel, right? It has to look at the previous pixels. And by stacking such causal convolutional layers, how they are called in this slide, one-dimensional causal convolutional layers, actually, and also having dilation, if you remember what is that, so how many pixels between windows we have, enlarging them, actually we can have very effective way of looking at previous pixels. Because if we stack 3 layers, so the output here for our probability, so predicting probabilities, so it will look 1, 2, 3, 4, 5, 6, 7 pixels just by stacking this convolutional layers. So this is very efficient, efficient way of learning long-range dependencies. No training issues whatsoever. The only drawback is slow generation, because this is an autoregressive model, right? So it's hard to do something about it. However, there are papers that show a huge improvement. And here to give you an example, so from 2018, these images are sampled from a pixel CNN specific pixel snail model with some attention mechanism and so on. But you can see how good these samples are. Of course, if you start looking closely, you can see that, well, this car is a little bit weird. Maybe this car as well. I don't know what is this, and so on. But in general, CIFAR10 is pretty crappy data set, 32 pixels. You don't see much. I don't see much at least. So these generations are really good, and this model is still used as an extremely strong baseline. Only up to recent papers, I think variational diffusion models and these very deep VAEs, so they were able to beat this model from 2018. So almost 3 years after introducing this model. So this is how powerful autoregressive models are. Okay. Right, so this is the first class of models. Now I would like to look at flow-based models. Okay, what these models are. Right. And flow-based models, they take advantage of completely different approach, right? And they actually take advantage of something that is called the change of variables. And to understand that, we'll look at a very simple example. Let's say we have a random variable, one single random variable that is Gaussian with mean 0 and standard or variance 1. Now, the question is, what will be a probability distribution of a new random variable? In this case, this is a random variable that somehow processes this z. And let's say that this is an affine transformation. So we multiply z by some scalar and we add some other scalar. If you know, if you are familiar with this kind of transformations for Gaussian, so probably you know already what is the answer here. But let us take this step by step. So to get the answer, of course, we can say, as I told you almost immediately, we can say, all right, so because we shift by 1, so we change the the mean, and then we multiply, so there is the variance, this difference. But how we can calculate this? So we can calculate it through the change of variables formula, okay? And the change of formula states that if you're interested in calculating the probability distribution of this new random variable, this is like taking the original distribution, where z is the inverse of x through some invertible function f, and we need to also change. We need to normalize this distribution, because it doesn't necessarily sum to 1 by change of volume. So the Jacobian of this function f, all right? And why is it so? Well, because this function f, even though it's a bijection, so it's invertible. So if I go from x to z, I can always go back to x, right? And there's never that 2 points will collapse to the same one. There are always 2 distinctive points. But this function f actually can take my small set and can make z that is really larger. So there will be this discrepancy between these 2 small set and big set. And because now it will create a big set, so I need to take it into account, because as I said, it not necessarily sums to 1. So we need to multiply it by the change of volume. All right, so this is this example. And so we can use this idea for d-dimensional spaces. And this is the crucial part of flow-based models. So if we look into a transformation, this actually should be the bold z. So we can start with, we can stack invertible transformations, and we can go from this z, so-called latent space, so simple distribution, into some pixel space that is very complicated, and we can go back by stacking invertible transformations. I always imagine that when I think about flows, I really see a pile of sand. Okay, so I can have this beautiful Gaussian pile of sand, and then my hands are this transformations f's. Okay, and if I, let's say, record my movements, so I can take this pile, I can move it a little bit, then separate them again, maybe flatten them, and so on. And then if you play in the reverse, so I can move my hands, and suddenly this will be back to this pile of sand, right? So this is exactly how this transformation f or transformations f work. Okay, they are invertible. I can play it forward and backwards. Okay, and also to remember, we go from this simple null distribution to a very complex one. In this, in some sense, not explicit way, right? Because we don't necessarily know what is p of x, but we can always express it using this transformation and simple distribution. So we always know, we can always learn through the log likelihood function. And for instance, a typical choice is Gaussian to take as the simple distribution, but of course, we cannot take any transformation f, because the Jacobian must be tractable, and this transformation must be invertible. So what we typically do, we just we just take invertible neural networks these days, of course. And the training objective is, as you already heard a couple of times, is the log likelihood function, right? And this is something that we can, if this is tractable, so we can calculate that. If this is Gaussian, so it's actually nothing else than the mean squared error, right? Logarithm with some maybe constants, right? So how we can, now the question is, of course, how we can formulate these invertible neural networks, right? So I will present you one approach. This is the approach proposed in the real MVP paper. But this is something like, a very good baseline, and there's a lot of work built on top of that. So this is really useful to know. So we can formulate, we can design a very particular specific layers that are invertible by design. So the idea is that we cut somehow the input into two parts, not necessarily of the same shape, but this is what is typically done. And then we treat the first part completely unchanged. We don't do anything with the first part. And then we transform the second part by scaling using the first part and by translating using the first part of this input, okay? So if you think about it, it's useful because first of all, we can very easily invert it. And what is even more, we can very easily calculate the Jacobian of this transformation. Why? Because if we calculate Jacobian with respect to xa, so here will be 1, and with respect to xb, so it will be 0. Then, so imagine that there's a big block matrix, so there will be identity matrix and just zeros. Then we will have this second part, yb and gradient with respect to xa. It will be something really complicated. But if you calculate now with xb with respect to xb, you will get diagonal block matrix. So on the diagonal, we have just ones and this xa, sorry, xa. And this we can calculate very easily, okay? Especially if we now take the logarithm of this Jacobian, determinant of Jacobian, so then logarithm will cancel out with exponent, and we just have sum of x's. So this is very good news. But of course, if we apply so-called coupling layers many times, so we would never change the first part, right? A simple trick to allow processing all random variables is just we can permute or flip the order. In permutation layer, if we know exactly what is the order, how we flip it or permute it, the determinant is simply a determinant Jacobian of this transformation simply 1, because it doesn't change volume, it just flips. It's like taking two axes and you just rotate them or something. So if you know how to do that, so you don't change the volume at all. Right, so this is a graphic representation of a composition of these two layers. So first we process it and then we flip it. And if we want to revert this transformation, so it is very easy to do. And in 2018, after the real MVP in 2016, I think, there was this GLOW paper that it was among the first papers that produced this very high quality images, realistically looking, that was a model that was trained entirely using the log likelihood function. So autoregressive models were unable to do such high quality images at that point. Now they are capable of that. And this was definitely a big breakthrough. Right. So this is about these two classes of models. And now, even though I know that you have a lecture about VAEs, this is some bunch of information that I hope that it will help you to see a larger picture of these deep generative models. And I personally, I'm really in favor of VAEs, and I like this methodology. So I think that it's good to see how we can deal with these models, especially that you saw that autoregressive models, they use this product rule as the main, methodological tool. Flows, they use this change of variables, and now in this VAEs you will see that actually we use the other tricks and the sum rule. Okay, so that's why I picked these three classes of models for you. So what are variational autoencoders. So they are models that can be classified as latent verbal models. Okay, so this is latent verbal models are models where we distinguish or we introduce some auxiliary latent verbals next to the observable variables. Okay, and this is motivated by a very nice generative process that you can summarize as follows: that there are some latent factors, some factors that are responsible for generating an image. For instance, like if we take horses, so we'll have, all right, the background is green because it's in the field in the summer or in the spring. The color of a horse is brownish or whitish. The height is this, you know, the weight is this, and so on. So there are a lot of factors that once determined, you can actually take them and conditionally you can generate an image. It's a little bit like thinking if I am a painter, I think about different features of something, and then I take my hand, P of X given Z, and I start painting, all right, and turn it into a painting. And mathematically speaking, these latent variables lie on a low-dimensional manifold, right? So this is some kind of a mathematical object that they nicely lie. Of course, not necessarily, it could be some lattice and so on, but typically we talk about continuous random variables, okay? And what is the objective? Of course, now it's a little bit more tricky. We are still interested in the log likelihood function. However, we have this joint distribution P of X and Z, right? Because now we say, all right, there are two random variables, and we cannot simply apply to this log P of X and Z, right? We cannot work with that. Why? Because these Z's are latent. We don't see them. They are unobserved. So what probability theory tells us to do? Well, it tells us that if you have something that is latent, you cannot observe something, just get rid of it, marginalize it out, sum it out, right? This will be then what you are looking for. And indeed, we do that. So to get P of X, we need to apply the sum rule here with the integral because of continuous random variables, but we sum over Z's, right, from the joint distribution. For this joint distribution, we applied again the product rule, right? So now I hope you see why this is so useful to know the basics. And everything is fine, but the problem is that this integral is intractable. If we have some nonlinear dependencies between X and Z, and for some distributions also even calculating these integrals could be intractable. So in general, we don't know what to do with that. But fortunately, we can apply some approximate inference. One is MCMC, and the other one is variational inference. And this is what we'll use for variational autoencoders. That's why variational, because we use the variational inference. So we start with the log likelihood function, sometimes called the log marginal of X. We multiply by 1 the inside, so we introduce something that is called variational posteriors. Then we rewrite it a little bit, so we take this Q of Z and divide this part, and then we have the integral with respect to Q of Z of something. So we can write it as the logarithm of the expected value of this P of X and Z divided by Q of Z. Then we use one of my favorite inequalities in mathematics, so the instance inequality. So it says that we can actually go with the logarithm inside the expected value, but then we get the lower bound, all right? Now applying, yes, so this is it. We need to remember that this is the lower bound. Then once we have the logarithm inside, so we can apply it to the product or the division. So we get this log of P of X given Z, so log conditional likelihood, the marginal over Z's, and the approximate variational posterior. And we can actually divide it into two parts, right? Because here is a plus, minus, so we can easily change the order and we can write it as two parts. And why this is useful? Well, this is very useful because the first part, we can say that this is the reconstruction error because we go from Z to X. right? So we reconstruct from given z. And we have the regularization term, which is something like naturally arising regularization term. And why? Because we know what is P of z, and the approximate inference, this is Q of z. So it is something like how close, what kind of mistake we do by taking this Q. Okay. And this lower bound is called the evidence lower bound. And also what is very important for variational autoencoder. So here I present you with this Q of z, right? But we can amortize this Q of z. So not for every single x we have one Q of z. We can amortize it and we can use Q of z given x. So it could be one single neural network that for given x will produce some z. And this is the real VAE, right? And also to have the real VAE, we need to use the reparameterization trick. Probably we'll learn more about it in the next lecture, but here it's actually good to know what does it mean. So we use this trick that every single Gaussian distribution could be expressed as mean plus the scaled standard Gaussian, right? So we can always move it and we can scale it. And this is actually very important because using the reparameterization trick allows to quite efficiently calculate gradients with respect to parameters for these expected values. So I mean efficiently because the variance of these gradients are way smaller. And why? Because we have this, we don't calculate gradients with respect to some randomness. The randomness is taken out from this equation, right? It's just independent noise, right? And it reduces the variance of the gradients, and it allows to get the randomness outside Z, as I said. So this is important to have mean and the standard deviation variance. And VAEs are extremely nice models. They are tightly connected to compression, data compression, for instance. They are tightly connected to autoencoders because they can be seen as a probabilistic autoencoders or stochastic autoencoders. They show that actually this variational inference could be very nice, and this is still very optimization framework. So for deep learning people, it's just a plug and play, almost just to think a little bit about distributions, and that's it. However, the problem of VAEs was that they produced pretty blurry images and not necessarily good quality of audio and so on. But recently, there is a huge progress and new architectures were proposed, so-called top-down variational autoencoders, or in some sense, yeah, we can call them, just put a label, hierarchical VAEs. And these very deep models, this is a paper from OpenAI, actually allow to produce, outperform autoaggressive models. And this is huge because VAEs, they have the latent space, they have latent code, and they can still outperform autoaggressive models. And so the potential here is enormous because maybe we can use them for representation learning, for maybe compression and so on, but still they are very good at producing amazing output. And a little bit of self-advertisement. So together with my master's student, it's already published in the journal Entropy, but we proposed a model that a hierarchical VAE that uses some deterministic non-trainable transformations, like for instance downscaling or edge detection that we call sketching. And then the generative procedure is actually very interesting because we first, for instance, we decompose the training objective into parts. And so first, because this is the pink path is fully deterministic, at least here, right? So then we can actually in the generative part, we can say that actually it's like learning decomposed VAE. So at each level, because for instance, this is downscaled version of an image. So it's smaller and smaller and smaller image. And at each level, we train like separate VAEs, right? And so it should be in theory easier to fit to some smaller models. Then the generative procedure is that first we sample, let's say very downscaled image, then we upscale it and upscale it in probabilistic fashion. And here are examples so that actually it works. So it's first we train this, we sample this images that are really downscaled. We don't see details, but we have this general idea about the image. Then we super resolute it, or how to call it, and it's actually getting more at the next level, more details. And then eventually we get the image, and you can see that actually these images are, of course, still because of computational resources, we couldn't do very high quality images, but here you can see that actually this quality is really high, and these images are pretty, crisp. But even more interesting was this with transformation that is just edge detecting. So you see that we have first we just, it's a little bit like asking a painter to first sketching a face and then putting colors with some paint. And this is very interesting because, for instance, I don't know what is the skin tone here or here or here or here. And then suddenly you see that, okay, this is more brownish, this is more, I don't know, lighter, a bit darker, pinkier, I don't know. And then here you don't see light on someone. And here, for instance, on the forehead, you can see that actually we have this a little bit light here. So at the next level, this model figures out what to put where, right? So I think that there is a big, very interesting model. And yes, so this is basically it for this. Of course, I could go on and on, but then my voice would be gone, and probably you would be completely tired. So if you are interested further in this topic, so of course, implicit models, GANs, you have a talk at 1:30, I think, from Danda Pani-Kaudel about GANs. You will have also about VAEs. If you are interested in GANs, you can also take a look at my blog post about GANs. And if you are interested about energy-based models, please go ahead and also check this out. And to conclude, why generative modeling, right? So I hope that maybe if you are not fully convinced, you started thinking about it at least. But I hope that you are convinced that actually we should focus on the joint distribution. All right, because this is how we work. We understand the world, P of X, and we can take some actions. We can make some decisions, P of Y given X. Of course, I completely skipped the part about how to model this joint. And for instance, one approach would be hybrid modeling. This is not the best approach ever, maybe, but this is one approach. There are others, of course, possible. And why we need this deep generative modeling? In my opinion, we can do without it. We can move further. So we really need better uncertainty quantification, and actually these probabilities alone can give us very good probabilities. We don't need maybe necessarily to be Bayesian. However, I am Bayesian at heart, but practically I am frequentist. And I think still that with deep generative modeling, we can get better uncertainty quantification, like this example with this black cross and two sources of data, right? By multiplying by P of X, we can get a better overall joint distribution. We definitely need new parameterization, so new neural networks. So this is not like I'm laughing at, or I don't know, disregarding deep learning. On the contrary, I think that we really need to understand what kind of neural networks we should use for parameterizing our probability distributions. It's actually very non-trivial, but yeah, we are getting better and better every day. Out of distribution is something like anyone solving this will be the next breakthrough, in my opinion, lies in out of distribution. We still fail, but we are getting better. And it seems that actually deep generative modeling is crucial for that. And this is something that the last topic, the continual learning problem, is definitely something that we must have if we want to talk about real AI. And by real AI, I mean an AI system that continually learns, doesn't forget, or at least doesn't forget useful information. And how to do that, I have no clue, but it's definitely my topic number one for the future. And I'm almost certain that deep generative modeling will play a huge role in that. And again, shameful, self-advertisement again. So if you are interested in the topic, first of all, look for the book that should be available in February. This is at least what Springer told me, February, March, let's say. But before, if you want to read about deep generative modeling, please go ahead, check out my blog posts. And yeah, the book, of course, is a way nicer version of this blog post. So thank you very much for the invitation, for this opportunity to give this talk and discuss ideas on deep generative modeling. I hope that you enjoyed this talk, and if you have any questions, just please let me know. Write me an email, and of course I maybe don't have time to answer immediately, but I really try to respond within 1 week, more. Okay, so thank you very much, and enjoy the rest of the summer school, sorry, winter school. Bye.